we are going to go through the notes here for lesson 3-3. Obviously, you guys know by now I'm not in class today. I'm still pretty sick, so I apologize for any coughing or sneezing that happened during this video. I will try to be quiet about it, but yeah. So we're just going to go through this as best we can. Watch the video, take notes in your notebook, just like if I was there. You can ask Miss Hain if you have any questions, or you can shoot me an email if you're not at school with Miss Hain. And I will do my best to answer your questions via email. When you're done with the notes today, you'll click on the link on Canvas that says assignment, and it is the 3-3 Math Excel online homework. So let's get started. As a review, now I've got a few things drawn out here. You do not have to draw all this out. This is just my way of doing a very quick review with you, okay? I'm in your notebook on page 177, just kind of using this blank space to do a quick review. So these are 5 different ways that we have seen relations so far. And remember, a relation is a set of ordered pairs, and then we can determine from that set of ordered pairs whether or not they're a function based on looking for any repeating cheating x's, and we can also determine whether or not these relations are linear or not. And we can decide whether they're linear or not by looking to see if there is a constant rate of change in the change in y over the change in x. So just really quickly, example number 1 is a linear. We know it's linear because it's in y equals mx plus b. And right from the equation, we can pull out that the m equals 5. And we can pull out that the b equals 10, right? We can pull that right from the equation. Looking at example number 2, first of all, is it a function? Well, it is. How do we know that? Well, we look at the x's, right? We look at our x's, and we don't have any repeating cheaters here, so we know that it's a function. Now let's test whether or not it's linear or not. Well, to do that, remember that if it's linear, we need to look for a constant change in y over change in x. So if you look at your change in y, because that's what goes on the top of the equation, right? Change in y over change in x. We look at how do the y's change each move, or from one point to the other. That is a plus 10. That is a plus 10. And that is a plus 10. So with each move, each point to point, the y increases by a constant rate of 10. Now let's look at the x's. Plus 2, plus 2, plus 2. So the x's change at a constant rate of plus 2. Because that's constant, we can say right now that it is linear, and we can say that the slope, when we reduce this, the constant rate of change, or the slope, is 5. Okay? This is just another way that you might be given a table. This table was side to side. This table's up and down. You still do the same thing. You look for the change, right? We go up 10. We go up 10. And we go up 10, and that's the change in y. On the change in x, we go up 2, up 2, up 2. So again, I could say that the m here is 10, which is the change in y, over 2, which reduces to a 5. Number 4 is just another way we've been given data, and it's just simply a set of ordered pairs. And it's, if you look at it, it's the same ordered pairs that's in the table. Okay, if you look at this point right here, 0, 10, that's right here. If you look at this point right here, 220, that's right here, and so on. So this is just another way that we can be given data. And then this is another way, and we've seen graphs. And from this graph, we could actually write an equation in y equals mx plus b by finding the m and finding the b. And we've already done all this. This is review. Remember that the b is the beginning point. Oops, sorry. The b is the beginning point, or where it crosses the y-axis. And so our b is 10. And our m is the rise over run. Well, if you pick any 2 points here, and I'll just pick these first 2 here, If I pick the blue point and the purple point, I look for the rise, right? The rise, which is a plus 10 over the run. So if I turn the corner and I run from here to here, which is a run of 2. So my rise over my run is 10 over 2, which equals 5, which means my m is 5. And with the m and the b, I can write the equation y equals, in place of the m, I'll put a 5, and in place of the b, I'll put a 10. So from a graph, from a table, from an up and down table, side to side table, and from an equation, we can pull all of this information. Now, all of these examples were all the exact same points. I do want to really quickly show you an example. I said that all of these were linear, and they were linear because the change in y, which was plus 10 every time, was constant, and the change in x was plus 2 every time. And because that was constant, I could write a slope, or a constant rate of change. Now, if we have a table with a different set of points, x and y, and let's say we do 2, 4, 8, 16. Okay, let's look at our change in y. From 2 to 4, that's a plus 2. But from 4 to 8, that's a plus 4. So we can stop right here. We can say that this is nonlinear, right? It's nonlinear because our change in y is not plus 2, plus 2, plus 2, plus 2. Okay? Is it a function? Well, let's look at our x's. Do we have any repeating, cheating x's? Nope, it is a function, right? Yes, it is a function, and it is an example of a nonlinear function. Now, what if I was to ask you to add another point to this table? Could you do it? Well, we can. We just have to look for patterns. The pattern in our x was plus 2, plus 2, plus 2, so our next pattern would have to be plus 2, so we would add an 8. Well, let's look at their pattern in our y. Now, our pattern, we don't have a pattern of addition and subtraction, which makes it nonlinear, but we can still pick up a pattern. 2 doubled is 4. 4 doubled is 8. 8 doubled is 16. So 16 doubled would be 32. So the next point in this pattern would be 832. Okay? We could do the same thing over here if we wanted to. What if I ask you to add another point to this table? We'll just follow the pattern. Plus 2, plus 2, plus 2. So we could fill in an 8. Plus 10, plus 10, plus 10. So 40 plus 10 would be 50. And again, this would continue to be linear because if we were to add the point 850 into our graph, it would be up right here. Okay, so from points in either a table, in a graph, on a sideways table, up and down table, doesn't matter. We can always find whether or not it's a function by looking at the x's. We can find whether or not it's linear by looking for a constant rate of change, and we can fill in extra points in the table by following whatever patterns we find. All right, on this first example, let's go ahead and turn to page 178 now. And on this first example, we're comparing, notice in this case, we're comparing two linear functions. Well, we know when we're comparing, the key word here is the linear. When we're comparing two linear functions, we know that we're going to compare the two important things in linear, which is the m and the b. So that means we have to find the m and the b. Well, we know how to do that. From a table, we look at the, right, change in y right here over the change in x. And so the change in y is 52 minus 20.8, which is right here. This is your change in y is right here. Change in y over. And then the change in x is going from 2 to 5, which we know is a plus 3. And that is your change in x, which goes on the bottom, and that's 5 minus 2 is 3. So we build a fraction, change in y over change in x, and we get this right here. And then when we reduce that by dividing 31.2 divided by 3, we get a constant rate of change of 10.4. So for the model T1000, these are two different robots that can build, what's it say? It says assembly factory, welding robots, and this is the number of welding tasks that these robots can perform per minute. And where do I get that information? I get that information from right here, right? It's the number of welding tasks that these robots can do per minute. And by getting it down to a 10.4 over 1, it's not really over 1, but it is. We don't write it, but it's there. It means that this robot can weld 10.4 tasks per 1 minute. Now if we look at this second robot, okay, the model GNX007, we're still given data, but we're given a graph. And so we still can find the M, right? We can still find our slope by looking for our change in Y over change in X, or our rise over run. And if we look at the rise from this point to this point, right, we rise, it's right here, 11.2. And if we look at the run from this point to this point, we run 1. So 11.2 over 1, which equals 11.2. So for this model GNX007, the M equals 11.2. And that is right here. So we can compare the rate at which these two robots do welding tasks. The blue one, or the model T1000, can do 10.4 welding tasks per minute, and the purple GNX one can do 11.2 tasks per minute, which means that the purple one, that the GNX007, that one can work a little bit faster because it can weld just a few more parts or do a few more welding tasks per minute. So when we're comparing these two, we first compare the M, or that constant rate of change. Remember, when you see constant rate of change, you need to think slope, and when you think slope, that's your M, okay? Now, the second part is comparing the initial value. Now, when you see, I don't know if you've really seen this term before, but when you see the term initial value, initial means beginning, and I know you guys have heard the term beginning value before, and we know that our beginning is our B, right? So we know when something begins, that's our B in Y equals mx plus B, and initial value just means beginning value. And this tells us that both robots at 0 minutes, and doesn't make sense if you start a task at 0 minutes is your beginning, right? So both robots at 0 minutes have performed 0 tasks. So both robots have an initial value of 0, or they both have a B of 0. So the data for the model GNX007 has a greater constant rate of change, or welding rate, okay? So it can complete more welding tasks per minute than the model T1000. And if we needed to write an equation for both of these, if we wrote an equation for the T1000, it would be Y equals, and then right here is its M, or its rate of change, so 10.4x, and then we've already said that both of them have a B of 0, so you can just put it there or leave it not there. And then we know that the this right here, this GNX007, we know that that equation would be Y equals, and then here is here is the slope for that one, and the slope would be 11.2x, and we also know its B was 0, so you could write it or not. So if you wrote it without it, it would look like this. And if you wrote the other one without the plus 0, because we know we don't have to put that plus 0 if it's a 0. Okay, those are the two equations that we got from finding the M, and we found the B. Now under this try it, it throws in a third robot. So if we throw in a third robot here, and it gives us the equation for that third robot. Now even though it didn't use Y and X, we still know that that's the M. So for robot 3, we know that the constant rate of change is 10.8, which means that the third robot can do 10.8 welding tasks per minute. And we've already seen that the model T1000 could do 10.4, and we have seen that the 007 can do 11.2 welding tasks per minute. So when it says, how does the third robot compare to the other two? Well, what you would write out as far as your answer is that robot 3 is faster than the the T1000 and slower than the, I'll just put the 007. Okay, so we can compare these three robots by comparing their constant rate of change or their slope, or how many tasks they can perform per minute. Okay, all right, so it says, how can linear equations help compare linear functions? Well, we've just shown that. We can take an equation, which is what we did right here. We took this equation, right? We built a couple other equations, and then we used those equations to compare the rate of change, or the m. And these were all the same. These were all plus 0. But if the b was different, we could also compare the initial value or the beginning value or the b. Okay? All right. In example 2, it says compare linear and nonlinear functions. Now, this comparison is a little bit different. Okay? Compare linear and nonlinear. Because if we're comparing two linear functions, they both have an m and a b. But a nonlinear function does not have an m, because it doesn't have a slope, because the very definition of slope is constant rate of change. And the only way that it can be nonlinear is if it's not constant, which means it's not going to have a slope. So we're not going to compare slopes. Really, the only thing you can compare is, are they functions, and are they linear or nonlinear? So when you're comparing one of each, kind of apples and oranges, the only two things you can question are, you can question, are they a function? And we know to answer that, we look for cheating x's. And then the other thing you can compare, or you can compare, is, are they linear or nonlinear? It's the only two things you can really compare between linear and nonlinear, okay? So let's look at these two bits of data, and again, one's given to us in a table and one's given to us in a graph, and that's okay. We can still find out everything we need to know. So this is your x's, this is your y's, and they've already done this, right? Let's look for, first, is it a function? 0, 1, 2, 3, 4, no cheating x's, so check, this relation is a function. And then we need to check to see if it's linear, and we know to do that, right? We look for the change in y over the change in x and see if it's constant. And in this case, the change in y is right here. It's plus 4, plus 4, plus 4, plus 4. Because it's a constant, always adding 4, we can say that the top number would be 4. And we look at our change in x's over here, and it's plus 1, plus 1, plus 1. So that's constant. So we could build a slope. Now, we are not going to compare slopes because we're not going to have a slope for the nonlinear one. But what we can say is, because we were able to build a slope, because we have a constant rate of change, we can say that this one is linear. Now, let's look at this one. Based on the graph, we don't even have to do any math whatsoever. Can we see it's a function? Yes, because it passes the vertical line test. And so right there, it's a function. And we can tell just by looking at it, because it has a curve, we can tell that it's nonlinear. Again, take zero math when you're just comparing a linear and a nonlinear, okay? Because we cannot find an m here. Cannot find an m here because m is only for a straight line or a linear equation, okay? So the only two things to compare, function yes or no, linear or nonlinear, okay? And in this case, this second one was nonlinear. All right, so example number 3 kind of jumps back to example number 1, because again, we're looking at comparing properties of linear functions. And what are the two properties that we can compare? We've already talked about this. It is the m and the b, right? Those are the two things, those are the two properties that we can compare. And a couple of different terms for m. We know that the m can be called the slope, right? And we know it can be called the constant rate of change. Okay, those are the two ways that we've heard the m called. And then the b, right here, the b, we have called it the beginning, right? It's our y-intercept. A couple of different ways that you have heard the b. It is the y-intercept. We've also called it the beginning, Okay, and those are all good ways. The other way that we have heard it up above is the initial value. And initial just means beginning, so it all means the same thing. So when you see the term like this, initial value, that's right there, right? That's your B. So here the B is -3, or the initial value is -3. And here, right, it says the constant rate of change. We know that's our M. Okay, so our M is 2 and our B is -3. Function A is given to us as an equation. Function B is given to us as a graph, but we can still find the M and the B from a graph. We find the M by looking, right, pick 2 good points. Find your, this is a fall over a run. It falls -1, it runs 2. So our M here is -1 over 2. And our B is, where does our line cross the y-intercept, right? Or the y-axis, right there. That's our beginning point because it crosses the y-axis at 7. So our initial value, or our B here, is 7. Okay, so when it says to compare these, always compare the M and the B. So your answer would be that function A, which is right here, function A was the equation. Function A has a greater what? Well, function A had a greater rate of change because function A's greater rate of change, or M, was 2. And function B's slope, or rate of change, was -1/2. So function A has a greater rate of change. I'm sorry, let's do that in red. Function A has a greater rate of change, that's your M. And function B had a greater initial value, or your B value. Okay, so that's how you compare them. You compare the M, say who has a greater M, and then who has a greater B. So this says try it. So we've got function 1 and function 2. Well, function 2 is easy. Let's do that one first. Our M for function 2 is right here. It's a 2. Our B for function 2, or our initial value, is -4, right? That's right there. So it's easy when it's given to us as an equation, right? We find our M, we find our B. Now what about in a table? Well, we can still find our M and B. It just takes a little bit more work, okay? So to find our M, we know that M, right, is our change in Y. Remember, triangle just means change in Y over change in X. So if we look at the difference between 1 to 5.5, what is the difference between those two numbers? Well, if you take 5.5 minus 1, you get 4.5. And it goes up, right? 1 goes up to 5.5, so that is an addition of 4.5. So I would say that the change in Y is 4.5. Now let's look at the change in X. That's here. It goes from 2 to 5. That is a +3. So I would put this over 3. And then if I take 4.5 divided by 3, I get 1.5. So my M is 1.5, okay, for function 1. Now I have to find my B. This is something we haven't done before. So we're going to take the equation Y equals mx plus B. And what we don't know right now is our B, right? That's what we don't know, and that's what we're going to try to find. But we know our M, right? We just found our M. Our M is 1.5. So since we know our M is 1.5, we can plug it into the equation for the M right here. So we can plug 1.5 in for the M. Now we need an X and a Y, and we have a bunch of X's and Y's given to us in this table because we know that this right here is an ordered pair. It's a point. And if I wanted to write this point as an ordered pair, we always write the X first and the Y second, right? This is an X and a Y. They're an ordered pair. And so I could put that X and Y into the equation. My Y value right here is a 1, so I would put that in my equation in place of the Y. Now we know this means multiplication, so I'm going to put it in parentheses here. My X value is a 2 on this point, so I'm going to plug a 2 in for the X. Now I still don't know my B, but that's okay because it's now the only thing I don't know. So I can actually use PEMDAS to solve for b. And the first thing I'm going to do is I'm going to take 2 times 1.5, right? Because I'm going to do the multiplication first. So I'm going to take 2 times 1.5, and that gives me 3 plus b. Now if I want to solve for b, I need to move that 3. So I'm going to minus 3 and minus 3. And when I do that, I get that b equals negative 2. So by doing a little bit of math, I know that my m for function 1 is 1.5, and I now know that my b is negative 2. So I have an m and I have a b. And to compare two linear functions, that's what you have to have. You have to find the m and the b for both. Now, how do we compare these? Well, what would we say? We would say that the, let's see, which one has a greater m? Okay, so we would say that function 2 has a greater, and I'm just going to put m, but we know that m means greater rate, a rate of change, right? But I'm just going to kind of use shorthand here. So function 2 has a greater m, which we know means the rate of change, and then let's look at our b. That means that function 1 has a greater, and again, I'm just going to put b for shorthand, but we know that b means initial value because the b was negative 2, which is greater than the negative 4 of function 2. So this would be my answer, right? If I'm comparing these two functions, these two linear functions, I'm going to compare the m and compare the b and say who has the greater, okay? All right, so this is just another example of that. Comparing, right? In an equation, we're given the m, we're given the b. That's easy. For the table, we have to do a little bit of work to find the m and to find the b. And here they've done the work to find the slope, right here, plus 3, that's our change in y, over plus 1. So the slope here was 3. And then again, look what they did. They took y equals mx plus b, right? They plugged a 3, which we know is our m. They plugged that into the m spot. And then they picked one of the points. They picked the point right here, 1, 4. And they plugged the 4, that's the y, into the y spot. They plugged the 1 for the x into the x spot. And then they took 3 times 1 is 3. And then they don't show the work here, but they minus 3 and minus 3 on both sides to make that go away. And they got b equals 1. So the b equals 1. Okay? Always goes back to y equals mx plus b. You can do a whole lot with that equation. And then you can compare these two. Okay? And then a third one here is same thing, right? You can find your m and your b. You can find your m by rise over run. We rise 5, we run 2. So that means that it's rise over run, and when we reduce that, we get 2.5. So the m here equals 2.5, and the b is the initial value, or the y-intercept, and so we know that the b equals 10. And now with that information, right, we have an m and a b for every single one of these, right? We have an m of 3 and a b of 1. We have an m of 2/3, and we have a b of negative 4. On this last one, we have an m of 2.5, and we have a b of 10. And with that information, we can answer any questions asked about these functions. Which ones has the greater rate of change, or the m? Which one has the greater b? Which one has the lesser b? Which one has the lesser rate of change? You can answer a whole lot of questions just by finding the m and the b. Okay? So I think that's about all I'm going to go with here on you. This is going to look a lot like your homework. You're going to be asked to compare, right? Two linear functions, I'm reading right here, two linear functions are shown. If you know they're linear, you know they each have an m and they each have a b. What are they asking you to compare? Well, here they're asking you to compare which function has the greater rate of change. So that's your m. So that's all you care about. Find your m, right? How do we find the m? Well, we rise and we run. We rise 1, we run 1. So the m here is 1. How do we find our m over here? We look for our constant rate of change. That's plus 3 over plus 2. The y is changed by 3. The x is changed by 2. When we reduce that, that's 1.5. So which function has the greater rate of change? The answer is function B. Okay, same thing here. This one's easy. This says 2 linear functions are shown below. What are they asking you to compare here? They're asking you to compare which function has the greater initial value. So they're asking you to compare the b's. Well, that's easy here. Your b here equals 3. What's your b here? Well, you can do the hard way. You can find your slope. You can plug it into y equals mx plus b. But on this one, they kind of give you a gift. They kind of give you the b. Not just kind of, they do. Remember when I told you when your x is 0, what does that make this? That makes that the b. So for the function a, here the b equals 4. Now if they didn't give you this x of 0, you would have had to have found the slope, picked one of the 2 points, plugged it into y equals mx plus b, and solved for b like we did over here, right? But because they gave you that little gift, they gave you this gift right here. When anytime x is 0, that's your b. So which linear function has the greater initial value or the greater b? The answer here would be function A. Okay, what are they asking you here? Pay attention because each one's going to be a little bit different. It just wants to know if each one is linear or nonlinear. Well, let's do the easy one first. This is a straight line, so this one's linear. Nice and easy. Let's check this one. Let's check our change in y. We go up 1, we go up 3. Oh, there's our stop. We don't even have to go any further. This one's nonlinear because we did not have a constant change. Okay? Okay, this one is tell which function is linear or nonlinear. That's the instructions here. Well, let's do the easy one first. Linear or nonlinear function A, that's easy. It's not a straight line, so it's nonlinear. Remember I told you anything in y equals mx plus b is linear, right? That's the very equation of a linear equation. Is this in y equals mx plus b? It is, right? Y equals, could I put 1x plus 0? So this is linear because it is a linear equation. And even though it doesn't look like it, there's a few things missing. That's kind of the bare bones of a y equals mx plus b. And your m is 1 and your b is 0. Okay? Determine whether or not each function is linear or nonlinear. That does not get any easier, right? Linear or nonlinear. Simply straight line, linear, not straight line, nonlinear. Doesn't get any easier than that, okay? I think that is all. Again, if you're given an equation, you know you can find your m is here and your b is here, okay? We know that we can find an m anytime you have a table. You can find your m plus 5, plus 5, plus 5, plus 1, plus 1, plus 1. So here our m is 5. Now again, how do we find our b here? First, look at the x's. They don't give you a gift of x equals 0. So you could do one of two things. You could add a point, and I showed you how to do this already. You could add a point, right? And we know that that's plus 1. And if we know that the change from this point to this point is a plus 5, that means this has to be 0. Now, if that doesn't make sense to you, you could also do it mathematically by the way I showed you a minute ago. You could take y equals mx plus b, and what do you know? You know that the m is 5, right? So we know that we can put a 5 in place of the m, and we can pick, I'll pick this point right here. That's an x and a y. So I'm going to plug it into my equation where there's an x and a y. I'm going to put the x in the x spot, so that's a 1. I'm going to put the y of 5 in the y spot, and then I'm going to leave this plus b unknown, and I'm going to find my own b. So I'm going to do a little bit of math here. 5 times 1 is 5. I'm going to minus 5 and minus 5 from both sides, and I get the same thing I got a minute ago. I get that b equals 0. So my b here is 0. So I found my m and my b from an equation. I found my m and my b from a table, and I can find my m and my b from a graph. Oops. The b is easy. Do that one first. The b is, where does it cross the y-intercept? The answer there is 4. My slope, find 2 good points. That's a good point, and that's a good point. So I'm going to do my fall, which is -4, over my run. Think about how much that run is. If here to here is 4, half of that would be 2. So my slope is a -4. That's my fall over my run of 2, and that reduces to -2. So in an equation, m and b. In a table, find your m and b. With a graph, you can still find your m and b, and you can still do any of the comparisons that you need to do. All right, I'm going to stop the video here. I know you don't have much time in class, but you've got about 10 minutes, maybe 5-10 minutes. You can start working on your Math Excel homework, and then if you have any questions, email me or go see Miss Hain throughout the day, and she can help you as well.